Hi, Alexi from Opto 22 here. Welcome to part 4 of our series showing how to use Opto 22's intelligent remote I/O with Allen Bradley Logic Systems. In this screencast, I'll demonstrate the built-in PID loop control capabilities of Snap I/O. Imagine running up to 96 PID loops on an I/O unit without slowing down your main controller. Of course, we realize there are other specialty loop controllers out there. The difference is Snap I/O does PID loop control in addition to all its other intelligent functions. Once again, I'll be using an Allen Bradley 1769 L32E Compact Logix controller, Opto 22 Snap I/O, and a load panel. Connected to the load panel is our PID simulator. It has a temperature sensor inside, which will serve as our input or process variable. It also has a resistor, which will function as a heater when current passes through it, so we can use it as an output to control the temperature. The set point for the PID loop will come from RSLogix software. First things first, we'll use our free utility, the Ethernet IP configurator, to configure the two I/O points we'll need and to configure the PID loop itself. Let's start with the temperature sensor, which is wired to module 3, so I'll double-click it. The type is analog input. The module is Snap AICTD, which stands for Integrated Circuit Temperature Device. This one only has 2 channels, but there's also an 8-channel version, which is ideal if you have a lot of temperature inputs for HVAC applications, for example. I'll double-click the first point. For the name, I'll type Process Temperature. I don't need to do any further configuration, as the Snap I/O unit is already going to report back the temperature in degrees Fahrenheit, so I'll click OK. The resistor I'm using as a heater is wired to module 2. The module itself was configured in the previous screencast, so I just need to configure point 1. I'll type heater control as the name. Now this module outputs -10 to +10 volts DC. We don't want to deal in volts DC, so we'll select the scalable option and click Custom. We want to work in engineering units of %, so I'll type that here. In this case, I'm going to map 0 volts DC to 0% and 10 volts to 100%. We'll click OK, and OK again. Great, we've got our I/O points. Let's move on to configuring the PID loop itself. I'll click the Configure PID Loops tab. The first thing you might notice, there's a lot of spots available here. You can configure up to 96 PID loops on the Snap I/O unit. We don't have time to actually do that many, so you'll have to trust me on that one. We'll just do one, so I'll double-click on 00. Here's the beauty of configuring PID loops on Snap I/O. You just fill in the blanks, and you can control flow rates, temperatures, variable frequency drives, you name it. Let's give our loop a name, like process control. The input for our loop will be the process temperature, our ICTD probe. But it could come from our PLC or the output of another PID loop, which is useful for cascading PID loops. Since we're dealing with temperature, I'll specify a low range of 50 and a high range of 100. These settings are useful for specifying a normal or valid operating range. Down here, you have options to affect the output when the input is outside of that range. Continuing with the configuration, you'll see that like the input or process variable, the set point can also come from an I/O point, the PLC, or the output of another PID loop. I'll choose PLC. In the real world, the set point might come from an operator interface or from the process itself. In our case, we'll enter a set point from RSLogix, and the PLC will send the value down to the PID loop on the Snap I/O. I'll set an initial value of 70. Next up is the output. I'll select the heater control, which we configured previously. All the analog output points are going to be listed here, as well as any digital outputs that have been configured as a TPO, or time proportional output. It's important to note that because the input and output come from points on the I/O unit, the Snap I/O can continue to control the temperature in the PID simulator, even if it loses communications with the PLC. Now I'll set the lower clamp at 0, since it doesn't make much sense to have negative 100% of the heater value. You might also use clamping to prevent an output device from completely shutting off or from reaching a destructively high setting. You can enter min or max change values. For example, a max change value can prevent a too drastic change in output. We'll keep the default of 0, which disables the feature. Moving on to the algorithm, you can see a variety of choices here. The formulas for each algorithm can be found in Form 1770, the Ethernet IP for SnapPack Protocol Guide. I'll keep the default of velocity type C. I'll also start off the PID loop in auto mode as opposed to manual. Now we come to the all-important scan rate. A couple of things I'd like to point out here. First, you can set a different scan rate for each PID loop. Have something with a long lag time? Put in a slow scan rate. Have a quick responding system? Put in a faster scan rate. Scan rates can go as fast as 1 millisecond. Also, these scan rates are completely independent of your Logix controller. Okay, now we'll enter some initial tuning parameters. Our heating system will require a negative gain because as our input, the temperature, decreases, we want the output, the heater, to increase, and vice versa. So I'll type -10 as a starting point. For the integral term, I'll throw in a small value of 0.05. We can refine these values or add a D term later during the tuning process. I'll click OK, and we've configured the PID loop. That's all SnapIO needs to run the loop. But if we want to be able to send a set point from RSLogix, for example, we'll need to create some assembly instances. So I'll click on the Configure Assemblies tab. Remember that assembly instances predetermine what data is sent between the SnapIO unit and the main controller. In the previous screencast, I arbitrarily decided that assembly instance 100 will read from the SnapIO unit to the controller. Let's add to the current assembly member. In the class field, I'll choose PID Loop Controller. I'll check the PID Loop name box and select our process control PID Loop. Over in Attributes, you'll see there's quite a few choices. In fact, every parameter that we configured for the PID loop is listed here and hence can be accessed from RSLogix. We'll select Set Point and click OK. Let's add another assembly instance to read in the input. PID Loop Controller and our Process Control Loop are already selected, so under Attribute, I'll select Input. Finally, we'll add one more assembly member to read in the output. This takes care of reading values into RSLogix, but what if we want to be able to adjust the set point from our process or from our Logix controller? Well, let's go to Assembly Instance 101, where we add data that we want to write to the SnapIO from RSLogix. I'll click Add. As you might guess, we'll select PID Loop Controller and our Process Control Loop. And under Attribute, I'll choose Set Point. We'll click OK. Finally, I'll click on the Verify tab, just to make sure all is well. This screen summarizes the number of DINTs, or double precision integers, that have been configured. We just need to download this configuration to the SnapIO. I'll click Download, verify the IP address, and click Download again. The complete configuration, including the PID loop, is now stored in the flash memory of the SnapIO unit. I'll close the dialog and save my file. All right, I'll go to RSLogix 5000, Rockwell Automation's programming language for their Compact Logix controller. I'm going to continue with the project from the Part 3 screencast. The SnapIO unit has already been configured as the generic Ethernet module, but we need to make a quick modification. In Assembly Instance 100, the inputs, we now have 6 DINTs that we configured in the Ethernet IP configurator. And in 101, we now have 3 DINTs. We're not using the configuration instance 102, so I'll just click OK. Now let's take a look at the controller tags. I'll expand the inputs so we can enter descriptions for the 3 new items we added. The first new element is the PID setpoint. The second item is the PID input. The last item shows the PID output. Moving on to the outputs, expanding the folders, let's update the newest item. From this field, we can write to the PID setpoint, so I'll enter that for the description. I'll also enter 70 to initialize the setpoint to 70 degrees. Let's try it out. I'll go to Communications, Download, to download the project to the Allen-Bradley CompactLogix controller. I'll click Download, and yes to run it. We can see that currently the PID input is about 76 degrees. The output is 0 because the input is above the current set point, 70 degrees. No need to turn on the heat. Now I'll raise the set point above the current value of the temperature, let's say 80 degrees. Watch how the output, the heater, turns on to raise the temperature. This is cool, but let me show you something even cooler. Let's go back to the Ethernet IP configurator. I'll click on the Configure PID Loops tab, and then I'll click on Tuning. Voila! The Ethernet IP configurator is plotting the data. Let's examine the screen. We can see the current values displayed up here. Better still, the input and set point are trending on this upper graph. Because they're close in value, let's zoom in a bit. I'll select Input Axis and 10% span. As the legend shows, the input or temperature is in red and the set point is in yellow. On the bottom graph, we can see the output, which is the heater. I can use the sliders to move the axis up and down. I can also change the time axis to view more or less data. Another neat feature is the cursors. These can be used to measure the time it takes the input to respond to a step change, or to measure the amount of overshoot, for example. I'll click on the Data tab and select Cursor. I'll right-click on the cursor and choose Style, Delta, Y. I can then place these lines at the points I want to measure. For example, I place the first line, tracking the input, and the second line at my set point. I can see there's an overshoot of about 0.42 degrees. To remove the cursor, I select Data and uncheck the cursor. Okay, let's briefly go through these tabs here. On the I/O details, you can see the specific configuration information, such as the name of the point that's the input or the name of the point that's the output. Not much under miscellaneous details, but let's go look at the velocity Type-C algorithm screen. Here we can see the algorithm and even watch the calculations. Pretty cool. Back here at the plot, you see that you can easily change the gain, integral, and derivative parameters. For example, I can increase the gain and click Apply. If you find great values for your PID parameters, you can just click the Save button, and these values will be permanently saved to the Snap I/O unit. Remember, all PID calculations are done by the Snap I/O unit, not in the Allen-Bradley PLC. Thanks for watching the final installment of this 4-part series of videos. You saw how to configure PID control loops on the Snap I/O and how to communicate to and from the PID loop from RSLogix. You also saw the great graphical tuning utility included with our free Ethernet IP configurator software. Be sure to visit Opto22.com for more information and to watch our other screencasts. See you next time!